In the study of thermodynamics, cold is not a physical substance that can be manufactured. It is defined strictly by the absence of thermal energy. This means an air conditioner cannot simply pump cold into a room. To lower the temperature, a system must physically capture the thermal energy already present in the air and move it elsewhere. We see this extraction process in biology. When we sweat, the moisture on our skin begins to evaporate. As the liquid turns into gas, it takes our body heat with it, leaving the skin cooler. This phenomenon is governed by the latent heat of vaporization. For a liquid to transition into a gas, it must absorb a massive amount of ambient thermal energy to break its molecular bonds. The liquid essentially steals this heat from its surroundings, resulting in a temperature drop. The process is reversible. When a gas loses kinetic energy and condenses back into a liquid, it sheds that trapped heat into its environment. Effective climate control doesn't require the creation of cold. It requires a mechanical method to weaponize and control these phase changes. The medium for this transfer is a refrigerant. This fluid is explicitly engineered to have an extremely high evaporative latent heat, making it an ideal vessel for carrying large amounts of thermal energy. To follow this process, we can visualize the refrigerant state using these indicators. Red and blue gradients represent temperature, while the density of particles indicates whether the fluid is a high-pressure liquid or a dispersed gas. As the refrigerant molecules absorb thermal energy, they expand from a dense, tightly packed liquid into a scattered gas. This highlights a central engineering challenge. Heat naturally flows from hot areas to cold ones, but an air conditioner must force heat from a cool room out into the even hotter summer air. To achieve this, the air conditioner operates as a four-stage closed-loop system. It mechanically manipulates the pressure of the refrigerant to force thermal energy to move uphill against its natural flow. By examining each component, we can see exactly how these thermodynamic principles are harnessed to control an indoor environment. The cycle begins at the evaporator, inside the indoor air conditioning unit. The system pumps cold, low-pressure liquid refrigerant into these indoor pipes. A space-saving cylindrical fan, known as an impeller, draws warm air from the room, forcing it directly over these chilled coils. As the warm air passes the pipes, the latent heat of vaporization takes over. The refrigerant inside the coils absorbs the thermal energy from the passing air. This heat intake causes the liquid to boil into a low-pressure gas, successfully trapping the room's thermal energy within the fluid. The indoor unit doesn't generate coolness. It acts as a heat thief, using a boiling fluid to strip thermal energy out of the air before blowing it back into the room. At this stage, the gaseous refrigerant is holding the room's heat. To get rid of it, the system must move it outside, where the air is already hot. This is achieved through a fundamental rule. Increasing the pressure of a gas inherently increases its temperature. The gas is routed to the compressor, located in the outdoor unit. Modern units typically use a scroll compressor. It features two interlocking spirals. One remains fixed, while the other orbits around it. Low-pressure gas from the indoor unit enters the outer edges of these interlocking scrolls. As the orbiting scroll moves, it traps the gas and forces it into an increasingly small space at the center of the mechanism. The gas exits the compressor in a highly pressurized state. Because the volume was reduced so aggressively, the temperature of the gas spikes to above 80 degrees Celsius. This component provides the physical work necessary to drive the cycle. By forcing the refrigerant to become hotter than the outdoor air, it makes the transfer of heat to the outside possible. This pressurized 80-degree gas is now sent through the third stage, the condenser. Because the gas is now much hotter than the outdoor summer air, thermal energy naturally begins to flow outward from the coils. Large propeller fans blow the outside air rapidly over these metal coils to greatly speed up the process of heat rejection. As the gas loses this thermal energy, its molecular kinetic energy drops. This energy loss forces the gas to condense back into a high-pressure liquid state at roughly 50 degrees Celsius. The condenser completes the handoff, effectively dumping the heat captured from inside the home into the outside environment. However, at 50 degrees Celsius, the liquid refrigerant returning to the house is still far too warm to cool a room. To drop the temperature instantly, the system uses a pressure drop, much like an aerosol spray can that becomes freezing cold after use. The expansion valve forces the hot liquid through an incredibly narrow opening. As the fluid emerges on the other side into a larger space, its pressure plummets. This causes the temperature to drop dramatically, resetting the refrigerant for another round of cooling. But the system must precisely control this flow. Letting too much refrigerant through could freeze the evaporator, while too little would fail to cool the room. This is regulated by monitoring sensible heat, thermal energy causing a measurable change in temperature, rather than a phase change. A sensible heat storage bulb, filled with temperature-sensitive fluid, is attached to the exit of the evaporator to monitor these changes. This creates a mechanical feedback loop. If the temperature at the evaporator exit rises, it indicates that the room's heat load is high and more refrigerant is needed. The fluid inside the bulb expands from this heat, pushing against a mechanical spring. This forces the expansion valve to open wider, increasing the flow of cold refrigerant. If the exit temperature drops, the fluid in the bulb contracts, the spring pressure is released, and the valve narrows to reduce the flow. This allows the system to achieve dynamic, real-time regulation of the cooling cycle without the need for digital controls. When we observe the system as a whole, we see all four components working in a continuous circuit. It is a constant loop of extracting heat through evaporation, increasing its temperature through compression, rejecting that heat via condensation, and resetting the process through expansion. While the refrigerant stays inside the pipes, its temperature has a secondary effect on the indoor air. Just as a cold glass of water collects moisture in a warm room, the freezing evaporator pipes interact with the air's humidity. As the water vapor in the room's air touches the cold pipes, it loses heat and condenses into liquid water. This water is collected in a drain pan and channeled through a pipe to be discharged outside. Ultimately, an air conditioner is not a creator of cold air. It is a sophisticated engine for thermodynamic displacement. By manipulating pressure and latent heat, it continuously captures thermal energy where it's not wanted and abandons it to the world outside.